Good afternoon, everybody. Thank you to the organizers for inviting me. I am delighted to be here. My permanent position is indeed in the Department of Statistics at Kansas State University. I do have a background in animal science and veterinary medicine, so much so that I'm currently in the Department of Animal Science at UW on sabbatical leave, so learning a lot. I was asked to talk about data analytics in the context of big data, and I debated how to go about this topic. There is a lot to cover. There's a lot, I think, that we are still trying to figure out. And I decided to focus on a topic that, at least I think... Okay, thank you. I decided to focus on a topic that, at least I think, in the years that I have been working on this topic, seems to be recurring and coming back over and over again, and that pertains to data architecture. So, with that, okay. With that, big data as a bigger framework for high-throughput phenotyping. We have heard a lot of the defining characteristics of big data today. Just to summarize them, certainly issues of volume, certainly issues of volume that have to do either with tall data, number of observations, wide data in the names of number of features, but just as much variety of the data. The type of data and the sources of data that we're dealing with also make for big data, and you can add to that issues of velocity, speed with which data is being collected and stored, as much as variability, biological, technical, experimental, as well as veracity, right? Issues of data quality. We're still in a world of junk in, junk out. So, due to developments in the technology of high-throughput phenotyping, in recent years we have had access to pretty large data sets that actually can be quite deceiving because they can be collected on a few animals and they can be really huge. So just to provide some examples along the lines of what we've heard today, I'm not getting the handle on this. Oh, okay. So let me try this then. Okay, so issues of spectral thermography to assess, for example, heat stress in cattle like we've seen today, or lameness. Data of the type of infrared spectrometry to assess body composition, biochemical composition of bodily fluids, for example, image analysis for diagnostics, for prediction of traits that might be complex to measure on the field. Also, video monitoring, for example, to record activities and behavior that can be expressed in different ways. Real-time sensors, as we just heard in the context of precision livestock, you combine that with weather data, and any and all of this can really make for pretty big data sets. Also in the context of big data, we have what we call operational data, meaning data that is regularly being collected on farms, on processing facilities, on slaughterhouses, and it's collected for the purpose of making internal decisions, not necessarily for research, but part of the question is, what else can we learn from it? We just heard about RFID. In the context of dairy, maybe one of the most typical examples has to do with dairy records management system. And there are others in other species, though probably a little bit more fractured. So any and all of these data sets can really make for really massive entities. Many are already available. Some can be relatively inexpensive to get, some of them, not all. And certainly the pre-analytic challenges, the pre-analytical component of this data can be quite challenging. Just issues of processing and storing and feature extraction can be by themselves quite intense. Now, once we have what we consider a clean data set to move on to learn, to actually try to understand some of the mechanisms that we're interested in, we're faced with analysis. And one of the typical tools that comes up with analysis is statistics. Well, we know that statistics was developed to assume the world of asymptotia for the most part, not to live in the world of asymptotia. So one of the questions that is currently being raised is, do we even need statistics? Isn't the data just enough because there's so much of it? Can sheer data size override statistics? This is a big question from an analytical perspective. I'm not going to pretend to get to the whole of it, but I do want to tackle on a specific aspect that has to do with data architecture and the role that it plays in the analysis of big data. Our data, as I'm going to show you, very typically has architecture. So we might wonder, is there a need to account for it? Can we disregard it? And if so, what are the practical implications of doing so? What I mean by data architecture, I am referring to the internal structure of the data. I'm referring to how the data is internally organized. And this is beyond the Excel spreadsheet, beyond the SQL file, beyond the Cyber's repository. I am talking about the process by which the data was acquired, the data generation process, which in the context of designed experiments, we have traditionally called the design structure of a data set. And usually this is dictated by the randomization process in a designed experiment. Observational data, like operational data, also has a design structure, though sometimes this can be a little bit more elusive to figure out. So, to develop some intuition on what I mean by data architecture, I suggest that we go through a couple of images. So, what I have here is what I would consider a graphical representation of multiple observations on a given outcome, multiple records. So the best thing I could come up with were vinyl records, okay? So multiple values observed on a response variable of interest. And the simplest scenario would be to consider that this data all these observations are mutually independent of each other. What do I mean by that? I mean that the value that, say, this observation here takes has no consequence for the value that any other observation in the data set has. This assumption of independence between observations is what we refer to in the context of design experiments as flat data, and it basically implies that I'm dealing with each observation as one independent piece of information. Now, in a more realistic setting, we know that observations don't live on the vacuum. They are actually organized and arranged in some way. So, for example, for a subset of the observations that I showed you in the previous slide, we might consider that some of these observations might pertain to the same animal, either because I had a single sample from each animal that was maybe measured with some sort of high-throughput phenotyping technology that yielded multiple values, say a spec mass type of phenotyping, or maybe we measured multiple tissues on that animal, or maybe we observed that animal multiple times over a period of time. Meaning then that all those observations collected within an animal are likely to share some common background that has to do with the physiology of that animal, some similarity, some commonality. I can take this to the next level, and I can consider that maybe the animals are not all living in the vacuum, but they are actually arranged and organized in some way. So I might consider that, for example, these animals are likely to be managed in pens, say, in groups. So that again, animals within a pen are likely to share a common environment that makes for commonalities in the observations between those animals. And of course, I can take this to the next level and consider that pens might be subjected to a typical, to a common type of business a decision structure that is decided at the farm level. So overall, I hope you can see that we can be arranging data in a multi-level fashion where I might have my observations, and there might be levels within the level here of observations that are nested within animal, which in turn are nested within pens, which in turn are nested within farms. So I am talking about hierarchically arranged data. Within each level, I might expect that observations have some source of commonality to them, some source of shared information. And if they share information, I can anticipate that then each observation is not quite an independent piece of information, so that the amount of information contained by each observation might be less than one for that observation. This is what we refer to as hierarchically arranged data. And these similarities, these commonalities in the data are going to be reflected by correlation patterns. Now, so overall, we find that many of the data we deal with in some way or another is characterized by multi-level architecture that reflects the way that the data was generated, and in turn, it introduces correlation patterns in the data. These correlation patterns are embedded, they are underlying. And interestingly, they are usually not the focus of the questions that we are asking. That doesn't make them any less relevant, as I'm going to show you in a minute. This realization of correlation patterns in the data is actually in stark contrast with many of the statistical methods that we commonly use in data, particularly those that are taught in introductory statistics courses. For example, certainly z-tests and t-tests and regressions and correlations and regular ANOVAs and chi-square type tests, and I would add even many of the machine learning methods that we are using, make the underlying assumption that our observations are mutually independent of each other, again in stark contrast with the correlation patterns that are embedded in the architecture of the data. So the oversight that these methods have in capturing that architecture can have implications for downstream inference. One of the main ones probably has to do with miscalibration of uncertainty on that inference. So just to characterize that in a very simple setting, if I have multiple observations that I assume to be independent, I can maybe try to summarize those observations with a mean and assess that uncertainty with a standard error or a variance for that estimator. In this case, the standard error of a mean can be shown to be given by this expression here, which I can write as a function of the true variance plus the covariance between observations. If I'm assuming independence, that means that in the linear world, this covariance cancels out, is equal to 0, and I end up with an expression of the variance that looks like this. However, though, if the observations are not mutually independent of each other, what happens is that these covariances don't necessarily cancel out, and the expression of my standard error for my estimator is actually given by this expression here. I still have sigma square over n, but now it's multiplied by an expression here that is a function of the covariance between my observations. If my observations were to be similar in some way, like we are assuming by common physiology and common environments, I can expect this covariance to be greater than 0, to be positive, meaning then that the true uncertainty on my estimator is going to probably be larger than under the assumption of independence. So if I assume independence, my uncertainty is actually underestimated. I'm thinking that I have more precise data than what I actually do. I can make a similar type of argument for group differences with a little bit more convoluted algebra, so the same type of argument holds here. There's another consequence for inference that has to do with amount of information available for inference. If we're assuming that our observations are independent, the amount of information is given by my sample size, n, the observed sample size. Now, if my observations are not mutually independent of each other, what's going to happen is that, like we said before, they probably share information. They are common in some way, so that each observation is probably less than one piece of information. I can express that in a very simple setting as an effective sample size, which has this expression here, n divided by this expression, which is a function of the covariance between my observations. Again, if the covariance is greater than 0, as I might expect given sources of similarity, what I'm going to find is that my effective sample size, the amount of information available for inference, is actually less than my observed sample size n. In more advanced inference, this is going to be reflected in the way of degrees of freedom, which are not going to be given by the number of observations, but actually by something else. So, in the overall, if I have data architecture in my data, and that data architecture is disregarded, there are a few implications for inference that are actually quite practical. One of them has to do with an underestimation of uncertainty, like I showed you, in the way of underestimated standard errors. The other one has to do with inflation in the amount of information available for inference. Combined, these are going to yield artificially large test statistics, artificially low p-values, which in turn are going to lead to inflated type 1 errors and an increased rate of false positives, meaning that data architecture that goes disregarded can easily yield my inference questionable at best. And I'll emphasize that this is inference on maybe a research question that was previously posed, that might be very sound, and its inference is undermined by data architecture that was not even the focus of the question to start with. Now, in the context of design experiments, data architecture is closely related to the concepts of experimental units, that good old friend. Experimental units, you might recall, is defined as the smallest entity to which treatments are independently applied. And it's absolutely critical that it be recognized properly, because we need experimental units to separate effects of treatments of interest to the effects of anything else that might be going on in our experiments. We usually separate experimental units, particularly from observational units, which are the entities on which our responses are measured, are observed, because very often in the animal sciences, the observation is not the experimental unit. Sometimes, in very simple designs, the two can be matched to the same thing, but in many cases they are not. When they are not, we refer to observational units as subsamples or technical replications. I'd like to illustrate this concept with a small example. You'll see it's certainly not a big data example at all, but it's illustrative, and I'll show you in a minute that it's easily scalable to a high-throughput phenotyping environment. So, let's pretend for a minute here that I'm looking at a research question that has to do with the effect of dietary protein content on weight gain of steers. I have three diets, high, moderate, and low levels of protein content, and I have 18 steers assigned to this experiment. My steers get fed one of the 3 diets after a period of feeding. They get run through the scale one at a time. I weigh each of them individually through the scale. So when I ask what was the unit measured, the steer is the answer that defines my observational unit. Now, when I think about the data generation process, when I think about data architecture, I need to, in addition, consider how these steers and treatments are organized, how they are arranged. And it might very well be the case that the steers were not managed individually, but they were actually grouped in pens. We most often feed pens, not individual steers. So what I had in this case were 3 pens, and you can see them color-coded here for each of my 3 treatments. 1 pen fed each different diet. So I have here, I might have a data set with 18 observations, and yet I have 1 pen per treatment. When I ask what was the unit to which the treatment was applied, what was my experimental unit, the answer is the pen. And with 1 pen per treatment, I have a problem with lack of experimental replication. Now, let's see how data architecture is interfering here. And I'm going to formalize this issue of lack of replication using a tool proposed by one of my colleagues, Walt Straub from University of Nebraska-Lincoln. Walt proposed a tool called What Would Fishers Do?, which is nothing but a modern version of an ANOVA table. The nice thing about it is that it's free of the arithmetic of sums of squares, of mean squares. That means that it is easily translatable to non-normal data, for which sums of squares are not even defined. And it's actually also very amenable to more complex designs, which can very easily get cumbersome in the context of traditional ANOVA. So, how does What Would Fishers Do work? What Would Fishers Do table has 3 parts. A first part that contains the topographical structure of the data. This is basically the architecture of the data. For my dietary treatment experiment, that topographical structure has to do with pens, for which I have 3 pens, 2 degrees of freedom, animals nested within pen. This is how my data is arranged, right, with 15 degrees of freedom. The next piece of the What Would Fishers Do table includes my treatment structure. What are the questions that I am asking, in this case, diet? And I'll mention that the relative position of the rows here matters. So I do want my treatments to be immediately above the element of the topographical structure that defines its experimental unit. So I need to put diet immediately on top of pen. Now, to combine, as a next step, I am going to need to combine these 2 tables. And to do that, I am basically going to slide both tables onto the right. I'm going to start with diet. I move it with 2 degrees of freedom. I then need to move pen. I'm going to slide it to the right. I had 2 degrees of freedom for pen, minus 2 that I used to estimate my diet effects. I am left with 0 degrees of freedom for pen. And finally, I have animal nested within pen within diet. So this is a data set for which I have 18 observations. You would think I have information to make inference. However, I have 0 degrees of freedom for pen nested within diet. So I have no replication for my treatment, even though I do have subsampling. So I hope you'll see that this is a case where if data architecture is disregarded, what I have is lack of recognition of no experimental replication in my design. If data architecture goes unnoticed, there's a design flaw that just gets overlooked. And I will argue that this is the case as long as we have 3 treatments, 1 pen per treatment. This is going to be the case regardless of whether I have observations in the teens, in the hundreds, or in the thousands. My data set can actually be very large and still suffer from a design flaw. Things can even get worse if I consider, for example, a case of high-throughput phenotyping where I might be collecting 100 observations, say, on spec mass for each animal. So I still have my 18 animals with 100 observations each. I end up with a data set of 1800s. My topographical structure here calls for pens, animals nested within pens, and observations nested within animals within pens. I slide them again to the right, and I am still having an issue with no replication, 0 degrees of freedom for diet, despite the fact that I have plenty degrees of freedom at the observational level. So again, issue of lack of replication that unless I recognize the architecture in my data goes completely unnoticed. So, all this to say that a lot of data does not necessarily mean a lot of information, at least not the type of information that we need to address the research question of interest, which again was about dietary treatment, meaning that if we have experimental units that we observe more closely or more frequently, that doesn't necessarily mean we are observing more replications. Now, how do we deal with data architecture? Once we have recognized it, how do we deal with it from an analytical perspective? Well, if our data has hierarchical levels, we might want to consider methods that inherently recognize those hierarchical levels. And hierarchical models are one possible choice, and a very natural one at that. In our discipline, we usually encounter them in the form of either hierarchical Bayesian models or mixed models, which can, when properly specified, can recognize data architecture by specification of random effects or by some sort of structure at the residual level. Now, these methods can get quite sophisticated. Fortunately, their implementation has been facilitated in recent years by much available software. However, though, this ease of implementation has been somewhat of a double-edged sword, because as much as the implementation of these methods has been facilitated by software, the specification of these models is not a task that is amenable to automation, to software automation. So, all this to say that mixed models and the recognition of data architecture is not a plug and play. To say that mixed models was used for an analysis doesn't necessarily indicate that data architecture was being taken care of. So much so, this is a very old problem. It's not new. I am standing in the shoulder of giants here, and to name a few, here's Ray Littell back in 2002. It's safe to say that improper attention to the presence of random effects is one of the most common and serious mistakes in the statistical analysis of data. And Walt Straub, translating the study design into a statistical model, is perhaps the most important facet in the practice of statistical modeling, also the most undervalued and overlooked. There's another spin-off of data architecture, and this is my last point, Jim, that has to do with scope of inference, how generalizable my results are. What is the population to which my results are applicable? And this has to do with data architecture that is properly recognized by the analytic method, not just by the fact that the data has architecture. And this scope can range from very narrow, maybe local within a herd. It can get broader, depending on basically what population is being represented. Regional, national, international, you name it. So why do we care? Data architecture from an analytical perspective. Well, I hope I have provided enough rationale to recognize that data architecture does introduce correlation patterns in the data. And this is directly related to defining the level of experimental replication that is needed for inference. Both of these pieces are critical to support the validity of our inference. And there's also, of course, the implication of where are our results applicable, scope of inference. It's not enough to have data architecture. We need methods that will recognize it, analytical methods that will recognize it. Mixed models are certainly one possibility, provided that they are properly specified. So a couple of take-home messages. Yes, we are in the era of big data. There's a lot of opportunity related to it. There are, I think, some issues to be aware of. First, data size is not necessarily the same as amount of information available for inference, because data size by itself cannot replace substantive knowledge. It cannot replace a thorough understanding of the data generation process, and it cannot make up for flaws in the experimental design. So I would personally argue that in the era of big data, these foundational concepts of experimental designs are as important as ever. So with that, I'd like to thank you, and if there's any time, open the floor for discussion.
Any questions for Nora?
Yes, Guilherme.
Nora, when you have a small data set, 1 or 2 variables, we go one by one looking at the distribution, look for outliers, see if there is any transformation on the data that it would be helpful. How we do this in the big data context when you have thousands or millions of variables and then you want to test, I don't know, multi-dimensional normality and so forth?
Right. What are the practicalities of data analysis for all these considerations, right? That's a very valid concern, Guilherme. I would say it probably depends on what your focus is. So if your focus is on prediction, we always have cross-validation to keep us honest, right? So we can assess how good our prediction tools are doing, regardless of the type of assumptions that they are making, how well they are doing through cross-validation. So I think that, from a prediction standpoint, that can be used to keep us honest and to get a feel for how relevant bypassing those assumptions might be, or how careful we need to be with checking those assumptions. From the standpoint of inference, though, when we're trying to understand the mechanisms, the biological mechanisms that generated the data, we are bound to the model, right? We are bound to the process that is assumed by the model, and we don't necessarily have a cross-validation approach to keep us honest. So from a prediction standpoint, I think we have that gauge of cross-validation to assess how worried we need to get about checking or not checking those assumptions. From an inference standpoint, I don't feel so comfortable with letting some of those assumptions go. We do know that there are some that are more important than others. We can check them, we can learn about them. In some systems, those assumptions might be more relevant than in others. I would feel a little bit more uneasy about making strong assumptions that have to do, for example, with architecture of the data when we're trying to learn the process that generated that data. And this is, of course, in the context of observational data. Once you have a designed experiment, the randomization process is dictating a lot of that data generation process.
I had 2 questions, and one is practically what Guilherme asked. This is an example of non-independence because I learned a lot from him. A lot of what I know, I learned from from my advisor once. So anyway, so I will ask the other one. Guilherme's question, by the way, is related to the variable-to-variable structure. And you talk not about the observation-to-observation structure that is obvious. So the question that I have left to ask is, how about cryptic subject-to-subject substructure in the data? So for example, and we start to have this problem a lot with big data, because we collect, big data might be, as you well explained, a lot of variables, a lot of individuals, or both. So now when we have a lot of individuals, there is metadata that is lost, and that leads to structure that if we recorded it, maybe we could put it in your model. But do you have any insights or recommendations how to diagnose maybe that we are missing some structure? Because I think that's a very pressing problem that we are seeing.
Oh boy, Juan. The more you know about the mechanism you're trying to model, probably the better you can approximate how well the model reflects that data generation process. There are also, what do they call them? Contradictory checks that you can do on your data. Sometimes you can, when there are results that don't make sense, you can go in and explore them at the individual level and try to understand what might have caused them to help you modify the model accordingly. There are risks associated with that, right? Again, from a prediction standpoint, you're not looking for the data generation process. You just want to predict, and cross-validation will keep you honest. From a inference standpoint, it can get trickier. And other than assessments of multicollinearity, I really don't have a better answer for you in terms of structure that spans on the wide level. Yes, and how do we deal with all these complexities? And moreover, how practically relevant is to deal with all these complexities? I think there's a lot to describe and work out there.
So unfortunately, we're going to have to cut it off because the shuttle is out here, and I think they're probably getting a bit antsy that we're not there yet. But let's thank Nora for a wonderful talk.